This is lecture 23 of Physics 210A, Thermal Physics. And in this lecture, we are going to apply kinetic theory to study some transport phenomena through kinetic theory. So, what is the kind of transport phenomena we are studying? We are going to talk about diffusion. We are going to talk about heat conduction. We are going to talk about electrical conduction and viscosity, and apply kinetic theory to obtain the corresponding constants, which I'll talk about in a few minutes. Now, when such a transport is taking place, then the system is not in equilibrium. System is not in equilibrium, and this implies that through transport of material or energy, the system tries to come to equilibrium. And if by some external agency you maintain that condition of non-equilibrium, then the transport keeps taking place. And we are going to study transport in a steady state. So let's talk about different phenomena that I have just presented. Diffusion of particles takes place when there is a density gradient. So what you have seen is, suppose I have a glass of water with some sugar in it. Slowly, the sugar particles start spreading and go throughout the water and become sweet, eventually the entire water. You can also see, if you have some water and put some colored powder here, potassium permanganate is a good example, and you see slowly the color starts spreading, so it's diffusing. Or you can also take some water and put raisins in it, kishmish. So raisins in water take in water through their skin, what is known as osmosis, and start ballooning up. So you see after some time their size has grown. So this is all diffusion phenomena driven by density gradient. We will now, for simplicity, consider phenomena in one direction. So what I am going to assume, and that will be good enough to calculate diffusion coefficient through kinetic theory. So suppose there is a density in the system that is changing with direction. So this is z direction, and here is n, the density, as a function of z. So what you see is that there is going to be a current of particles in the direction opposite to the density gradient, and the current, diffusion current, Jd, is given as minus d grad of n. This is known as Fick's law. And in the 1D case that we are considering here, you will have J z equals minus d dn dz. And if you maintain this gradient, the flow is going to be steady. Here, J is the diffusion current, that is number of particles per unit area per unit time, and d is diffusion coefficient. So this is an empirical law. Similarly, if you talk about heat conduction, this you are familiar with from your 12th grade. Now, just like the gradient in density gives particle diffusion, similarly gradient in temperature gives heat diffusion. So what you have studied in your 12th grade is, if I maintain two ends of a conducting material at temperatures T1 and T2, and there is a dt dx in the middle, then you get the heat current, that is energy passing or heat passing per unit area per unit time, to be equal to exactly like Fick's law, minus k grad of T, or in the present case it's going to be Jx equals minus k dt dx, where Jx is the heat current and k is thermal conductivity. So it's exactly like diffusion of material. Third, we have charge conduction. whereby a current density, again you have seen it from your 12th grade, gives rise to, a current density is given rise to by gradient in the potential, where sigma is conductivity and V is the electric potential. And the form you have seen it in is J equals sigma E, with E being electric field. So you have to apply an electric field, and that gives rise to a charge transport from one side to the other. Finally, I'm going to talk about viscosity, which is like frictional force acting at interface between two fluid blocks, if you like, due to velocity gradient. So if you have, say, some fluid flowing like this with a velocity gradient, so I have dvx over dz not equal to 0. Then if I take some fluid here and some on top, on the lower fluid there will be a force in this direction. This is the viscosity force, viscous force, and Fx is going to be equal to minus eta dvx dz, where eta is the viscosity. So these are four phenomena that I'm going to talk about. So let's start doing that. So all these calculations will be done by considering how the particles or molecules of a substance behave under the condition for the processes described above. And we'll be doing these calculations under certain assumptions. So we'll assume that the gas we are considering is dilute. So only two molecule collisions are considered. And when I'm talking about collisions, what I'm assuming is that molecules do not have any interaction between them except when they collide. That means if I take two molecules, there is no interaction. The only interaction is when they collide. And this is only between two. Now, 2. The average time between two collisions is tau, known as the mean collision time. And with this, the probability of two molecules colliding in time interval dt is dt over tau. You can actually derive this result considering all the probabilities and everything, but we are not doing it right now. Third, the average distance traveled between collisions by a molecule is L, known as mean free path. Four, after each collision, molecules are in local equilibrium. That means the density at that point is given by the local conditions. And number 5, after each collision, molecules have random velocities. So they are in local equilibrium and they have random velocity. So under these conditions, let us now calculate diffusion coefficient. So we'll now before that, let me ask you a question for diffusion. So the question is, difference in which thermodynamic property between two places causes diffusion to take place. So this is a question for you to think about. So what I'm going to do now is perform this calculation exactly like we did for the pressure. So perform the calculation of diffusion current like we calculated pressure in lecture 22. So now what is happening is that given a point, so suppose I have a point somewhere, the molecules that are coming in had their last collision on an average at a distance L. So they bring in whatever properties are coming in are according to the equilibrium properties at this distance L from that point. So this is all L. And in the present case, let us take the direction shown by red to be Z direction. And there is this density gradient. So there is NZ. So whatever properties are coming in are determined by N at these different points here on this hemisphere. So particles coming from all these different points give rise to a current here. Particles coming from the left give rise to a current here. By symmetry, Jx, Jy will cancel, and you have a net current going down. Similarly, there will be a current from the opposite side, and the difference or the vector sum of the two currents will give you diffusion current. So let's see now how do we proceed with the calculation. So in this semicircle, or hemisphere, here is this point, and here is the hemisphere. Consider the direction from vertical to be theta. And this is where we'll take the particles coming in from and form a current here. Let this area be A, and the projection of the area perpendicular to the direction of particles coming, let this be A projection. All the information that is coming is from this point. So the density we'll consider will be at this point for particles coming from this side. Now let's calculate the number of particles coming in at speed v from this theta angle. So number of particles is going to be, the density will correspond to the previous collision place. After that, density doesn't change on an average, and no information about the density beyond this point. And therefore, the number of particles coming in at speed v is going to be equal to n. Since density varies as a function of z, so z is going to be z plus L cosine theta. Let me show where L cosine theta is. This is L cosine of theta times the velocity v times the area projection AP. Now, just like in the previous calculation, the probability that particles are coming from this direction is going to be d omega over 4 pi. This we have discussed in the previous lecture, so I'm not going to do it again. So, with this probability, these particles are going to come in. And finally, there is this distribution of speed, so that particles with speed between v and v plus dv have fraction this. So distribution function is fv dv. I'm not spending much time on this because this I had done in the previous lecture. So I have the particles coming in, I have the distribution, and I have the probability. So let me make this figure again. Here is this area, and the particles are coming in from this angle theta from here. This cross section perpendicular to the direction is AP. This vertical is L cosine of theta, because this angle is theta. This is L, and therefore the number of particles coming in through AP is equal to N L plus Z cosine of theta V AP d omega over 4 pi, and these particles are this fraction fv dv of the total fraction, and therefore the current J and J direction is going to be as shown here. So let me bring it here. J in this direction shown is going to be equal to integration, V integration is going to be from 0 to infinity fv dv. I'll divide by A, so that will be N L plus Z cosine of theta. Oh, sorry, I'm writing it the other way. It should be Z plus L cosine of theta. This is Z. So this is N L Z plus L cosine of theta times V. I have divided by AP d omega divided by 4 pi. That's the J coming in. Let's write it as delta J. So let me write it again. Delta J is equal to integration 0 to infinity dV fv n Z plus L cosine theta times V times d omega over 4 pi. And this is in a particular direction. So if I were to calculate Jz, this will be equal to summation of all these delta J cosine of theta, because that will be the component in Z direction. And this is going to be equal to integral, dV integral is there, fv dV n at Z plus L cos theta times there's V here, times d omega over 4 pi cosine of theta. And we'll calculate this. Now, L is very small, so I can do an expansion and I also assume that the gradient of n is small, so n z plus L cosine of theta can be replaced by n z plus dn dz L cosine of theta. And therefore, Jz from the upper half, so let me write this upper, is going to be equal to integration dv fv v. This I can write separately, nz d omega over cosine theta, d omega over 4 pi times cosine of theta over this half sphere, plus the second term. So let's do that on the next page. I should also, since I'm taking it coming down, so I should also put a minus sign somewhere. So let's make this minus. This is minus. So considering this hemisphere and taking these current coming in and taking its z component, the net Jz upper is going to be minus integral 0 to infinity dv fv v. And then I have nz integration 0 to 1 cosine theta d cos theta, and then there's a 2 pi, so it will be divided by 4 pi, it will be 1 by 2. And the second term is going to be minus integral 0 to infinity, this part remains. Then I get dn by dz. Then I have L, cosine theta will go in, then I'll have 0 to 1 cosine square theta d cos theta times 1/2. So this current comes out to be minus dv fvv is nothing but v bar. So nz v bar divided by 4. This is the flux that we had calculated in the previous lecture. And there is an additional term which is minus 1/6 dn dz L v bar, where v bar is equal to integration 0 to infinity dv fv v. Now exactly in the same manner, we can calculate current Jz coming from the lower side. And this will come out to be nz v bar by 4 minus 1/6 dn dz L v bar. So this is a current going in the upper direction. And you add the two, and you get the total current. So the total current Jz comes out to be J upper Z plus Jz lower, and this comes out to be minus 1/3 L V bar dN dz. So through all this calculation, we've learned that Jz is equal to minus 1/3 L V bar dN dz. Now, before I proceed further, let me ask you a question or give you an exercise. Show mathematically that Jx, both from the upper side, Jx lower, Jy upper, Jy lower, all vanish. This is an exercise I am giving you. So, because of density gradient dN dz, we get diffusion current Jz equals minus 1/3 LV bar dN dz. And comparing with the Fick's law gives D equals LV bar divided by 3. That's the diffusion coefficient. This is diffusion coefficient in terms of the mean free path and average speed V bar. So this calculation was exactly like what we did for pressure or flux, except that now an additional term came because there is a gradient in the density, and that additional term gives you the diffusion current. If there was no gradient term, the average flux going from lower side and the upper side will cancel and there will be no net flux. But now because of the gradient there is a net flux, and which is nothing but diffusion. Now exactly in the same manner, we can also calculate the thermal conductivity. So let's do that now. I'll not do the full calculation, but give you indication as to how to do it. Now you see this, if I compare diffusion and heat conductivity or heat diffusion, because I wanted to make this comparison, that's why I earlier said that you can think of particle diffusion as heat diffusion also. So in the diffusion case, I took this hemisphere of radius L and calculated the particle current J. In the present case, what we want to do is again consider a hemisphere of length L, but now what will happen is here is some temperature T which depends on Z. So at this point, the point shown by red, I'll have T, if this place is Z, Z plus L cosine of theta. And it is this difference in temperature that's driving the current. And what will it be transporting? It will be transporting energy. So instead of particles, now the energy is transported. So, in the diffusion case, if you look at this point, I was considering n at z plus L cosine theta, and this n was giving me the particles. So, here what I will consider is the energy of the particles. Here we consider energy of particles per unit volume, and that will be CV T z plus L cosine theta, where CV is specific heat per unit volume. Before proceeding further, let me ask you a question. Why am I using CV to get the energy per unit volume? And not Cp. So, instead of N, it is CVT which is being transported. So, in heat diffusion, N is being replaced by CVT. Now, diffusion current was minus 1/3 L V bar dN dz, and therefore, since I am replacing N by CVT, the heat current is going to be minus 1/3 LV bar CV dt dz, and this gives the heat conductivity to be 1/3 L V bar CV. That's your answer. Now, I like you to obtain this by going through detailed calculation, just like we did for diffusion. Do it for thermal conductivity also. So, obtain this by going through detailed calculation. I have given you the answer. So, what we have done in this lecture is calculated the diffusion coefficient and heat conductivity through kinetic theory of gases. Limitation, of course, is that the gas is dilute, so that collisions are limited to 2 particle collisions, and then we have taken a mean collision time to be tau and mean free path. So, with this, let me conclude this lecture. Diffusion coefficient and heat conductivity for gases have been calculated using kinetic theory. Thank you.